Now that we can solve simple kinematic problems, we need to start looking at more advanced ones. For example, the one on the board. The space shuttle takes off in stages. At the first stage, which lasts 7 seconds, provides an acceleration of 1.33 meters per second to the initially at-rest shuttle. Stage 2 lasts 53 seconds, taking the shuttle to a velocity of 125 meters per second. How high up is the rocket after stage 2? The problem here is that all of our equations work only if the acceleration is constant. When we have a changing acceleration like we do here, we have a problem. Thankfully, there is a fairly easy solution for this. Start with the graphic organizer of the GoCast method, and then everything else that happens from there becomes fairly apparent. So the space shuttle starts initially at rest. So if I'm drawing a velocity time graph for it, it would look something like this for stage 1. After stage 1, the acceleration changes. The reason I know this is many different ways, but the base idea here is because I'm talking about different stages, the assumption is that there will be different accelerations. Whether or not it is, we have to treat it as such. The other way I know this is because there's different times given, different durations. Continuing on. This is how high up, what's my displacement after this time frame. Now, when I look at this graph, it's fairly clear that there's this change in slope right here. And if I can find all my values, I can find exactly my displacement via the area. I know that this is 125 at the end. I know this chunk here is 7 seconds. I know this chunk here is 53 seconds. All I need to do is find this little section here, and I can find everything else. That's how I do it graphically. But how would I do it as an equation? Well, there's a couple different ways. Regardless of how you handle this or think about it, you have to split it into 2 separate problems. You'll have stage 1, and then you'll have stage 2. In short, whenever the acceleration changes, you need to use a different set of equations, or you have a different set of given. My initial velocity here is not my initial velocity here. Stage 1's initial velocity is not stage 2. There's another way to say that. But there is some things we can carry over between the problems. Let's start with stage 1 in red, and just pay attention to that. From stage 1, my givens I'll underline in red. Let's see. It tells me that it lasts 7 seconds, which would be a time. It tells me that the acceleration is 1.33. And it tells me it starts at rest. This is not a number, but it does tell me it starts from an initial velocity of 0. This becomes very helpful in scenarios down the road. Whenever you see at rest or to a stop, you know there's a 0 somewhere in the problem. My unknown in this case is I want to know how far it goes. Now, finding out how far it goes is just a simple matter of using one of my equations at this point. In this case, my unknown is delta x. Now, if I'm looking at this graphically, in order to find my delta x, the first thing I need to find is this v final. If I'm going at it from the equation, I can find the equation that ties all these together directly, and I don't need to solve for that v final. Either way will get you there. We'll go through both. To start, let's talk about how we solve this graphically. Then we'll go through and talk about how we solve with equations, and you can pick and choose. To start solving graphically, what we need to do is we need to be able to find the area of each section. The area of these two will be fairly easy to find if you use the area of the trapezoid. If you don't use the area of the trapezoid, you need to find this line here, which is this velocity after stage 1. Once you find that, you can find everything else. In order to go through this, let's start by finding that velocity. We know from definition and from experience that A equals delta V over delta T. In this case, we're talking about stages 1 velocity. I don't care about the 125 currently. All I care about is stage 1. So this entire section isn't particularly helpful. To solve for delta V first. And then delta V is always V final minus V initial. Which means that V equals V initial plus AT. Which is just the equation we have on our kinematic sheet anyways. Doesn't affect us too much. We could have shortcutted to get here. From here, well, you can plug in my numbers. V equals 0 plus acceleration, which is 1.33 times 7. V equals, go ahead, plug it in, is 9.31 meters per second. Now from here, it's just a graph. We have 3 parts. Let's label them 1, 2, 3, and we just need to find all those areas. Area 1 was 1/2 base times height, or 1/2 times 7 times the 9.31. Area 2 is base times height, which in this case would be 53 times 9.31. Area 3 is this triangle, which is 1/2 base times height, or 1/2 times 53 times your delta V, or 125 minus 9.31. Once you got all of these, add them in your calculator. And you can do it all in one expression as long as you make sure you use your parentheses and put your plus signs where they're appropriate. If you go through and do all this math appropriately, double checking to make sure you did it right, you should get 3,591.8 meters. And that's how we do it graphically. Draw the graph, split it into parts, find the missing information we need, and go from there. It's still the go-guess method. We still find our givens, we still find our unknowns, but there's a stopgap in the middle where we need to find this missing point. On the other hand, let's talk about how we solve this as an equation. When you're looking to do an equation, we need to be able to break it into stages. Every time you have a new acceleration, it's effectively a new set of problems, a new set of givens. So we'll start with the red for stage 1, and then we'll do stage 2 in blue, and we'll see how things carry between them. So for stage 1, my givens are already underlined. I underlined them for the graph, and just left them up there. So once again, we've said time is 7 seconds. Acceleration is 1.33, and V initial equals 0. Since I'm looking for delta x, my unknown will be delta x. That's how far I want to go. And my equation, in this case, that ties these 4 variables together is delta x equals v naught t plus 1/2 a t squared. Which, if you'll notice, since my initial velocity is 0, this is just the triangle area. Same idea, same thing. Plug in my numbers. And I should get 32.5 meters. And that's this section. Stage 2 only cares about from here over. So let's go ahead and talk about this. From here over. What are my givens? Well, for stage 2, I know that it lasts 53 seconds. And then it has a taking it to, which tells me it's an ending velocity of 125 meters. So v equals 125. T equals 53 seconds. And what I'm looking for is how far. So my unknown, in this case, is delta x. And here we hit our problem. We only have 2 variables in our unknown. All of our equations use 4. We can't use any of our equations. We won't be able to get an answer. We're stuck. We're lost. We're screwed, for lack of a better term. We can't solve this via equations unless we cheat. If we look back at our graph, we'll notice that stage 1 ends at here, right here. But stage 2 starts here. Whatever velocity I ended at stage 1 at is the velocity I'm starting stage 2 at. In other words, when I move between stages or move between different steps of a problem, whatever the first section of time ends at, the next starts at. This would also continue forward. If we had a stage 3, whatever stage 2 ends at, stage 3 starts at. And because the velocity of an object is continuous, it doesn't suddenly teleport. If you step on the gas in your car and bring your car up to 60 and then let off the gas, you don't suddenly stop. You start slowing down from 60. You're still at 60 once you let go of the gas. With that in mind, the V final here will be the same as the V initial here. So if we can find that V final, we can find that V initial. So let's find the V final. If we come back over here to stage 1, we need to find that V final, but we have our givens, 3 givens, and we have our delta x. We have all 4 other variables. We can pick whatever equation we want to make our life easier. I could use the V final squared equation, which is often known as the stopping equation. I could use the V equals V naught plus AT equation. The only equation I can't end up using is this one because it doesn't have V final or V by itself anywhere in it. This equation doesn't help me because it doesn't have V. Any other ones are a fair game. For ease of math and to make my poor easy brain better, first thing I'm going to do is I'm going to label this as A because we're solving for 2 unknowns. So the unknown B in this case would be V equals V naught plus AT, which, if you think back to the graphing, is how we solve that. Plug in everything, and surprising no one, we'll get the same number we got when we solved it graphically, which in this case is 9.31 meters per second. So the 9.31 meters per second here, that is my final velocity of stage 1, becomes my initial velocity for stage 2. And I can carry that over. And now I can solve. I can find an equation, substitute and solve, or solve and substitute. So in this case, the equation that ties together V, V naught, delta x, and t isn't on the equation sheet for AP, but it is the equation I gave you last time, which is delta x equals V naught plus V for 2. if you don't want to memorize this equation, if you don't like this equation, what you'd need to end up doing is use these variables here to solve for a, then plug in to one of your other equations to solve for delta x, either the v squared equation or the delta x equals v naught t plus 1/2 at squared. Or you can use this equation if you happen to memorize it or have written it down. It's already solved for delta x, which is my end goal. So I can plug in my numbers. Naught is 9.31. V final is 125 over 2 times 53, which gives me 3,559.215 meters. Now, you'll notice that this isn't the answer we got last time, because that's just for stage 2. What I need to do now is add my two answers together. Give me a total for everything. 3,591.81 meters. And while this is a little different than we got last time, 0.81 versus 0.80, that's probably a rounding error because we had to use a number here that rounded elsewhere. Same answer, two different but related ways of solving it. However you want to handle a two-step problem, either via a graph or equations, will get you there. Personally, I'd rather do the equations, but I'm weird. The graph is probably quicker for some people. Do what works best for you. Do both, because especially if I start asking other questions, such as what's the acceleration? Well, then you have to go back and solve the entire thing again. Whereas working with the equations, you have the numbers set aside, and you can go back easier. Graphs are better for single answers. Equations are generally better for multiple different answers. Additionally, graphs are really bad at getting slopes or accelerations easily, but they're very good at the areas, whereas the equations are very good at finding every single thing. It just might take a little bit longer. Now, not only can we use this to go forward, if we were to go to stage 3 at this point, we could talk about how it starts at the velocity of whatever we'd have to solve for here, or given to us of 125. We can also work backwards. Okay, we know this information about this, what happened before. For now, let's look at a practice problem. You're driving down the road. Maybe you're going to a party or school at 20 meters per second when you realize you're late. You're going to be late. So you step on the accelerator, provide an acceleration of 2.17 meters per second squared. However, after 8 seconds of accel, you see a friend broken down on the side of the road, waving for help. You, being a good friend, decide to stop. Step on the brakes, giving you an acceleration of negative 3.43 meters per second. Negative because you're slowing down. How far do you go before you stop? Draw a graphic organizer. Find your givens, find your unknowns, break it into 2 stages, and get going. Okay, let's start this one from the top. I drew a graphic organizer. You start going 20 meters per second. You end here. On the second part, I drew a steeper slope because you're slowing down faster than you were speeding up. So this should have a steeper slope here. For regulars, this isn't particularly important. For AP, this detail does matter, so make sure your graphical organizers are appropriate. From there, I went through and solved the problem. My givens are 20 meters per second, 8 seconds, 12.17 meters per second. I'm solving for V. I didn't bother to solve for delta x because it only asks for how long it takes me to stop, which is here. It doesn't ask anything about during the accelerating phase. So once I found the V, once I figured out I was looking for V, I found my equation, which I put with a typo that I've quickly fixed, plugged in my numbers, solved for V. The V that I end stage 1 at is the V I start stage 2 at because I'm traveling at the speed before I let off the gas and step on the brakes. So my givens are 37.36 for my initial, which again is my final here. Just draw an arrow, make that very clear. My final velocity is 0 because I am, as it says right here, before you stop, I have this negative 343 meters per second squared. I'm looking for how far, which would be a displacement delta x. Only equation that ties all those together is my stopping equation. I'm not particularly surprised because I'm asking how far did you go before I stop. So typically whenever you hear stopping, probably going to be this. I rearranged and solved first. Look at my numbers and get 203.46 meters, which means this area here is 203.46 meters. Had you done this graphically or split it, once you got the 37.36, you'd be a little SOL. You need to find the time from the graph before you can solve this graphically. In this case, the equation was probably quicker. There you have it. Thanks for watching. Have a good one.